Hello, everybody. So, this is going to be the central limit theorem for proportions, and I'm going to break it up into potentially a couple videos. So, the first thing I'm going to work with is discovering why it's the case that I don't know why that disappeared, but why the mean, and this is notation you're going to need to get used to, the mean for the sampling distribution of sample proportions um, is actually equal to just the population proportion. So, first thing we need to understand is what p hat represents. It's akin to x bar, um, and it's the sample proportion. And p hat is x over n, where x is your number of successes and n is your sample size. Okay, so um, what we're going to do is we're going to not necessarily prove it, but we're going to try and show you how it happens with an example. So we need to characterize our heads and our tails numerically. Um, this is something that gets done throughout statistics. So we're going to treat 1 as heads and we're going to treat 0 as tails. So it's often the case that what we're focused on gets the 1 and what we're not focused on gets the 0. It doesn't have to work that way. You can flip it if you want to. But for our purposes, 1 is heads, 0 is tails. And so if this is our population, we have the option of heads, we have the option of tails. We're going to use the probability formula for determining the mean, where we take the sum of x times px. And our first x is 1, and that can occur half the time. And the second x is 0, and that can occur half the time because the 1 is the heads and the 0 is the tails. And so we're looking at an overall probability of a half. And so this actually, our population proportion, we're going to see, is going to end up being our mean of our sampling distribution. So what is a sampling distribution? Well, the sampling distribution is, first of all, you set a number of observations that you need to have. Normally it's more than 30, but I can't make a tree diagram that would have 30 options, so I'm going to do 3. So we're going to set, in this instance, our n to be equal to 3. We're going to be doing 3 possible uh, pulls. And we are doing it with replacement. So what could happen is you could have 3 t's, and that would mean you had 0 successes out of 3. You could have 2 t's and an h, 1 out of 3, 2 t's and an h, but in a different order, and you have 1 out of 3. And then you have 2 t's and an h, and yet again a different order, so you have 1 out of 3. So our proportions of successes in each of those instances is 1 out of 3. And then we have the same thing for, oops, that's supposed to be a 3. Not 2 out of 2, 2 out of 3. So we have 2 successes, we have 2 successes, we have 2 successes. And finally we have 3 successes going on. All right, well, how do we generate that? Well, to generate the actual sample space, which is technically what this category here, or this column A is, we basically made a tree diagram. And we have heads, then tails, so that's our first draw. We could have heads, then tails, heads, then tails. That's what could happen after our second draw. And then heads, then tails, heads, then tails, heads, then tails, heads, then tails. And that's what could happen after our third draw. So This one here is draw 1, this layer here is draw 2, this layer here is draw 3. Now, when we look at our number of paths that have all heads, well, that means when we're talking about our samples, we have one path out of the 8. There are a total of 8 paths here. Have 3 successes out of 3. There are 3 paths out of the 8 that have 2 successes out of 3. There are 3 paths out of 8 that have 1 success out of 3. And we have 1 path out of the 8 that has 0 successes out of the 3. Now, I already canceled the 3's and canceled the 3's there. And so we have this 3 over 3 actually being equal to 1. So what occurs is I have 1/8. Let me do this in a different color. So I have 1/8. And then what I'm going to get out of here is 2/8. So I have a 1/8 from the first one. And then I have a 2/8 from the second one. And then from here, I get a 1/8 again. And so I end up with a response of 4 out of 8. And when we reduce that, we end up getting our 1/2 again. So what ends up occurring, and this is the conclusion that we need, at least for the first part, is that the mean of the sampling distribution of sample proportions, the mean of the sampling distribution of sample proportions is actually equal to the population proportion. Okay, and I hope that gives an example as to why that's the case. All right, I'm going to stop the video here, and I'm going to make another one for why the standard deviation is the way the standard deviation is. All right.